In this video, we will show how dynamic zoning works in a simulated manufacturing floor environment with genetic algorithm, simulated annealing, and decentralized dynamic zoning. The diagram in the top right of the screen shows the current zone design. The dots represent workstation locations, and the colored lines show each individual zone. Each line is a floor segment connecting the workstations within a zone. What is being shown now is the start of the genetic algorithm. Both simulated annealing and genetic algorithm start by first finding the initial zone design. Once that is found, the robots move to pick up and drop off parts at workstations. It's important to note that this simulation is done with NVIDIA Isaac Sim and the NVIDIA Carter robot. Here we can see the manufacturing floor layout. It is divided into two main sections, the warehouse area shown by the racks to the left, and the production/assembly areas shown by the large yellow rectangles. The robots used in the simulation are autonomous mobile robots, or AMRs. These robots are capable of finding alternate routes to move around obstacles once they are detected. This will be demonstrated by placing a red block in front of the robot's path. The trajectory path is shown as a green line and is constantly updated. The robot will continue to the next workstation, where it will drop off a theoretical part. Once the part is dropped off at the workstation, it will enter the workstation queue where it will wait to be processed. After the part has finished processing, the part is then added to the robot queue where it will be sorted by shortest job first with aging. This sorting method prioritizes parts based on the shortest completion time, while also taking into consideration how long a part has been in the robot's queue. After some time, and after an imbalance has been detected, the algorithm will go into zone repair. During zone repair, the system will restart genetic algorithm or simulated annealing to find the optimal zone design based on the current recorded data. In this case, the optimal zone design is one that most balances the load of each robot. Decentralized dynamic zoning is different since it cannot rely on a central unit to manage the robots. In DDZ, once a robot has detected an imbalance for some time, it will enter zone repair. The robot that initiates zone repair will then send a message to neighboring robots that halts their movement and tells them to enter zone repair. During zone repair, the robot takes turns running simulated annealing with its neighbors, trying to find the zone design with the lowest standard deviation of load. Prior to starting zone repair, the average load between each robot is found by weighted average consensus. The measured average is then used in the standard deviation calculation. To show the differences between each algorithm, we ran 100 parts of varying routes through the system. For a simulated annealing, or SA, and genetic algorithm, GA, they completed the simulation in around 6 hours, with GA having a higher throughput. DZ, on the other hand, had a lower throughput throughout the simulation and took 2 more hours to complete. This can be explained by DDZ not being able to load share, which is a feature in GA and SA that allows robots to bypass transfer stations and deliver parts into the next zone. DDZ, however, was able to achieve a much better distribution of tasks, which is shown with the deviation in total travel distance. This 68.7% decrease shows that AMRs were able to move at a similar rate throughout the simulation. This could be very useful in a real-world application of DDZ, since it will be easy to design a charging and maintenance schedule around the robots.